Okay, welcome to the session. The title of my talk is Authenticated Encryption for Very Short Inputs, and I'm Kazuhiko Minamatsu, and this is a joint work with Alexandra Adamunkai and Junji Shikata. All right. So the content of my talk is as follows. So I first described a very basic fact about the authenticated encryption is, and then we move to our research question, namely the performance overhead for really short inputs. And we proceed to our proposal, which we call the MANCS, and they provide the security and the security analysis and the implementation result. And finally, we conclude. Okay. So what the authenticated encryption is? It's basically a symmetric key encryption function that provides the encryption and method authentication code functionality at once. Namely, it provides the confidentiality of the plaintext as well as the integrity of the whole input of the ciphertext. And it has been now widely deployed to major communication protocols. So most typical, the famous one is the TLS deployed on the internet. And of course, most of the encrypted communication now today are more or less using authenticated encryption. So let me describe the syntax of the AEs here. So basically, we have encryption function of the authenticated encryption takes these four variables. The K is the key, N is the nonce, which is a value that never repeats while in encryption, and associated data, ADA, which is part of the input that is not encrypted but must be authenticated, such as like the protocol version over receiver address or so on. And the M is the plaintext. And taking these four variables, encryption outputs the C and the T here, and the C is the ciphertext, and the T is called tag, and which is a variable used to verify the authenticity of the whole input to the decryption function. And the decryption takes these five variables and outputs the plaintext if the whole input tuple is valid. And otherwise, outputs the bot symbol, which denotes the error. So it detects, that means that it detects the forgery between these four tuples. So in this talk, we focus on the AE built on the block cipher. Typically, say for example, that we can build model operation using the AES. And we also focus on the cost, simply the computation cost. And the most typical measure for measuring the cost of the authenticated encryption and other model operation is a rate, which is the inverse number of the block cipher codes that is needed to process one input block. Say, for example, there's a GCM, which is a NIST standard. It needs one encryption code, a block cipher code, plus one 128-bit multiplication. So depending on the multiplication, cost of the multiplication depends on the platform, but if we simply assume it as equivalent to the block cipher, it means that we need two codes here, so the rate is 1/2. On the other hand, there's a very nice model operation, which is called OCB, developed by, the latest version was developed by Crobes and Logaway, and now standardized in the RFC. And this scheme has 1E, so rate is 1, which means that encryption and authentication done in just one core per one input block, so it's quite good. Actually, this hits the theoretical speed limit because we always need at least one block cipher code to one input block for encryption, just for encryption. Okay? In the sense, we cannot do better in terms of the rate. So this rate but expresses the speed for the sufficiently long message. So this ignores the constant terms. But what if the input messages are short? Then because the rate ignores the constant computation overhead, so that does not reflect the actual performance for short inputs. And we want to say that actually this computational overhead, it matters for many protocols. Because that some modern, say, IoT-like protocols use very short input packet lengths for various constraints. Typically the power and typically the bandwidth, because and these are correlated in most cases. So, say for example, the Sigfox, which is a kind of famous, popular IoT, devices, and it has a 12 bytes packet length. And we list here some examples, say in Ocean, which is an energy harvesting devices, and not for the IoT device protocols, but say RFID or a QR code has a quite short input constraints. While the AES has just a 16-byte block. So this suggests that the following question. So are the current standard with AES enough fast for under such constraint of the input length? So based on these observations, so we consider authenticated encryption modes dedicated to very short inputs. Actually, this problem on the importance of the short input E has been acknowledged by existing researchers, but their proposals keep generality, meaning that they are proposing some authenticated encryption scheme, but their proposal can handle the long inputs as well. But we would like to take a more aggressive step, one step further, by abandoning carrying the wrong input. So we just focus on designing an authenticated encryption that can handle short inputs. So to design such a mode, we first need to look into the what the performance of the current AE modes are in terms of the short inputs. Okay? So for example, GCM, in case of the, we measure the minimum number of block cipher codes for any non-empty messages, including the pre-computation. Then GCM needs a 3E plus 2 multiplication, and OCB, while it has a rate 1, but the computational overhead is 4 block cipher cores. And there's another mode which is called COFB. It needs 3E cores. And as far as I know, there's no known modes that performs better. So this suggests that following natural question, so what AE is then possible with just 2 block cipher cores? To put it more specifically, we define the 3 parameters. But the first is the nonce length nu, and the associated data length alpha, and the message length L. And our question is to search explore the space of these tuple nu and alpha n that can be supported with associated or AE just using 2 block cipher cores. That's our question. And we propose a solution to this problem. So our proposal named the Manx, which is a family of AE modes, needing just at most 2 cores, 2 block cipher cores, and there's no pre-computation and no rekeying, and it has a standard model security based on the standard pseudo-random assumption on the underlying block cipher. So the name of the Manx is also a name of the feline cats, a kind of cats that have a really short tail. So yeah, okay, that's why I named here. There are the 2 members, the Manx 1 and Manx 2, and especially Manx 2 is, I think, interesting because it allows to encrypt almost n bit, where n denotes the block size of the underlying block cipher. So it's also small, but it is not extremely small. So I hope it could cover a wide range of applications in real life. And it also achieves the what is called the birthday bound security, namely the half of n-bit security when it is used, realized with an n-bit block cipher. And if you are familiar with the provable security things, you will learn that this security level is comparable to what the current standard achieves. Okay, let me go to the move to the baseline scheme. Actually, because we are considering the A scheme using two block cipher codes, it's natural to first consider what can be done just one code. And there's a classical scheme known as the encode-then cipher proposed by Berare and Rogaway in 2000. Then the scheme is here, so extremely simple. So we just concatenate nonce and associate data in the plaintext and encrypt it. The output is C, and we send the N and A and C here. And the receiver decrypts this C and see if the first new bits part is as expected. Namely, if it is equal to the N sent in the clear text, it is successfully decrypted. This works. But if we let the sigma denote the total input length, namely the sum of the nu and alpha and L, and this only works if sigma is at most n. Of course, the finality because the input length is n. So the next question, natural question here is what to do if sigma exceeds n. And we can use one block cipher code. And the first solution here is Manx1 is actually built on a model operation called XEX proposed by Rogaway. And it turns a block cipher into a so-called tweakable block cipher, which is a form of an extended form of the block cipher. So it has additional input here, and it can encrypt n-bit block. So you can see here that V1 and V2, and it is a result of some encoding of taking the N and A. And we put the second variable V2, its length must be no shorter than some tau, which did not define the security level we want to achieve. Okay? And so the encryption and the decryption scheme is quite similar to the previous encode-then and cipher. So we compute the C here and send N and A and C, and we can decrypt the C and see if the V2 is as expected. So this actually extension it allows a longer nonce than the previous encode-then cipher because the nonce, here is a result of, because it's a result of the encode function and the total input length of the encode output is something n plus tau at least, so longer than n. So we can say we can use a longer nonce. At the maximum, nonce length can be almost 2n. Which may be useful for certain cases, say nonce are generated by randomly. But on the downside, the plaintext length is at most n minus tau, and the tau denotes the security level, which usually something close to n, at least half of n in typical case, if we use the AES, for example. So this implies that the message is significantly shorter than n. That's a limitation. And in addition, it needs two serial block cipher codes for any plaintext. Even if the plaintext is just 1 bit, we need the two serial block cipher codes. So it's not a good situation, I think. So to solve these two drawbacks, we propose a Manx2, where in Manx2, the two block cipher calls are in parallel, and it supports this plaintext length, so 2n minus 2 nu minus alpha approximately. And if we set the new nonce as half of n bits and alpha is negligibly small, it implies that L is about n. And it's also another additional feature that if the L is really small, actually more specifically smaller than this threshold, we just need one block cipher call. So there's no waste. Okay, the Manx2 is here. Actual scheme is something more complex because we need some encode and decoding schemes applied to these input variables. So please refer to the paper for the full spec here. But in any case, so the Manx2, in Manx2, we perform, it has two operation modes. The one left-hand case is what we call the tiny message case. So the message is really short, so that the full encode Zen cipher can be used in that case. Now, otherwise, we switch to the right-hand mode shown in the right-hand side. And in this case, you see that mostly the two parallel encode Zen cipher scheme here, but as you can see, the message is divided in two parts, M1 and M2, and the nonce is given to the both input. But associated data is just inputted into the left-hand side block cipher call. And in case of this short message case, the sender receiver will receive this tuple A and C1 and C2, so we can omit sending N in clear text, so which saves the bandwidth. And for decryption, maybe it's obvious, but yeah, we first perform the decryption for both block cipher calls and get the expected value of the nonce here, and we see if both values are matched, identical or not. Okay? So I'd like to comment that this pretty simple mode has some structural similarity to the RPC mode proposed in Katz and Jung in 2000 FSC. So really old. RPC is actually one of the earliest proposals of the A mode operation. So, but it has a larger overhead and a larger bandwidth, so it's anyway classical. But what I see that what we are doing is visiting old and finding learning some new things. So we analyzed its security and we proved it is secure. So maybe, but unless you are an expert in the area, so this figure may be a bit hard to what it tells. So, but I would say that the first equation, Adobe Preview, shows that the confidentiality of the scheme, and the second equation denotes the integrity or authenticity of the scheme. So, and these values shows roughly the success probability of the attacker in terms of the confidentiality and integrity, authenticity. So, and we show it is bounded by certain terms, depending on the security of the block cipher and the resource number of the queries that the adversary can issue. Okay, and I'm skipping into what the actual meaning of these parameters are, but the main message is that these inequalities shows that both Manx1 and Manx2, for Manx2 with half of n bit nonce case, both schemes achieve the half of n bit security, and which is comparable to what OCBO and GCM achieves. Okay, and in the rest of my talk, I would like to show some implementation result. And because the main purpose is some IoT or sort of these tiny input use cases, so I think it's natural to focus on the benchmarking the platform with microcontrollers. So we took the 8-bit AVR at Omega 128 and 32-bit ARM Cortex-M4. Both are quite widely deployed in the field of the IoT-like protocols. And we took AES as a baseline block cipher, and we used for 8-bit AVR. We took open source AES implementation, which is, I guess, still the fastest implementation of 8-bit AVR. And for 32-bit, we adopted a fixed slicing implementation, which is a modern implementation of the bit slice implementation, and achieves the fastest constant time implementation on most of the microcontrollers. A unique feature of it is it enables a 2-block parallel operation. And we implement under Monks on these platforms and compare with non-block cipher modes of operation. So the results are here. So we selected several parameter cases for the, say, for example, the first row shows that 64-bit nonce and 0 associated data and 120 bits message length. And the second one and the third one you can find here. And as you can see that the Monks clearly shows the performance advantage over any of the existing modes, just because we just need 2 block cipher calls, while the others are at least needing 3 block cipher calls. So it's quite simple. So actually, in each case, we see a gain from the 30% to more than 200% from the closest competitors. And Monks 2 is mostly because of its parallelism, it's always faster than Monks 1. Okay, yeah, so this mode may be useful if your application or protocol has a very short inputs and packets and you really need better performance while keeping the security of AES, for example. Of course, if you want to get more performance, you can switch to from AES to or more lightweight ciphers, say Gifter or any other block ciphers. It's up to your choice. If you believe, if you have your preferred block cipher, you can use it as long as it's believed to be secure. Okay, to conclude, so in this talk I provided a Monks, which is a proposed family of A modes dedicated to very short inputs, and this started from the naive question. So what can we do within 2 block cipher cores? And I think that Monks fills the gap between the most primitive form of the AE, namely the encode then encipher, and the general purpose AE. So there are some future directions, say composition or integration with general purpose AE would be interesting. Namely, say if Monks is used for very short inputs and OCB is used for longer inputs, then it could potentially improve the average speed of the underlying protocol if the message length varies from short to something longer. And of course, this problem can be extended to the case if we use other primitives, such as the tweakable block cipher or cryptographic permutations. Okay, that's ongoing work. Okay. So that's it. Thanks for your attention. Yeah. I'm happy to answer any question.
Thank you, Kaze, for a great talk. I think it's nice to have these types of results at RSA because it shows how you can overlap with something like cryptography, but also practical results. Yeah. Really appreciate the implementation results. Can you maybe go to that slide?
Yeah.
So I see minus there. I guess that's Alexandre who did the implementation. Can you explain for Monks 1 on the first on the top part, why there are no speed benchmarks for...
Yes, simply because it doesn't it cannot handle this parameter, right? Because the new, we want to achieve, in this case, the tau, the security level is set to the 64-bit, just half of the block cipher. And in this case, that okay, Manx1 has this structure, and 64-bit will be put here. So that means that the plain text is at most 64-bit, so it can't handle this
Okay,
parameter.
thank you.
Yeah.
Hi, so thank you very much for the talk. So I also have one more question. So as far as I listen this talk, so I think Monks 2 is always better than Monks 1. So why you propose Monks 1?
That's a nice question. So yeah, basically I agree with your opinion generally because plain text length is anyway an important parameter. So if you can support just 1-bit plain text, it has almost no application, I guess. But in case of the Monks, because of this structure, it allows some useful case that cannot be covered by Monks 1. Because, say, for example, that if nonce is almost n-bit, Monks 1 still can handle it because the V1, we just set the V1 equal to the nonce, and V2 equal to, say, or 0 or associated data or encoded part of the associated data or sort of. But in case of the Monks 2, if we set the nonce being n, we can't handle simply, Or plain text will be really short. So there are some trading off, and Monks 1 and Monks 2 are each areas that can support it. So and they are different, not covered each.
Okay, thank you very much. I understand.
Okay, if you no more questions, I can finish my talk. Thanks.
Is it start? Okay. Okay, so the second talk is keyed sum of permutations, a simpler random permutation-based pseudo-random function. So I am Yosuke Todo at the NTT Social Informatics Laboratories. And this is a joint work with Ferdinand Simulators. It's the same affiliation. Okay, so I skip here. Okay. The topic is about idealized construction. So it means we want to build a new primitives from other primitives. So I think as a so maybe as a cryptographer know this. I think that these two constructions is very famous for cryptographers. But so I want to just introduce what is this. So the first construction is Evenmancer. So it's a very famous constructions to build pseudo-random permutations from random permutation. So now P is a random permutations, and this is a fixed random permutations. So now we want to build pseudo-random permutations, the so-called block cipher from the random permutation. Then how to do it? So first, X is a plain text, and we have the key, secret key, and X plus key, and this XORed value it becomes the input of the random permutations, and this output is XORed with key again, and this output is a ciphertext. So by using this construction, so that we can convert random permutation to pseudo-random permutation. And another famous one is Facile network. So it's a very famous structures. And so that actually is DES adapt to these constructions. So this is a construction. This is a method to build pseudo-random permutation from pseudo-random function. So pseudo-random function is, of course, a function. So it's not permutation. So it's not so bijective. It means if we use pseudo-random function directly for the block cipher, we no longer decrypt. So now we want to convert as a pseudo-random function to pseudo-random permutation. Then how to do it? So fk1, fk2, fk3 pseudo-random function, then we first the input is divided into two halves, and one side is the input of the pseudo-random functions, and this output is XORed with another side, and swap, and then repeat this computations. So Ruby Rakoff proposed a very nice proof. So actually, so in 3 rounds, proves the three pseudo-random permutations, and 4 rounds is just SPRP security. So today's topic is similar to this type of discussions. So, but our focus is how to build pseudo-random function from random permutation. So this topic was introduced by these authors at Crypto 2019, and the random permutation-based pseudo-random functions. Actually, so this motivation is, for example, if you want to use this primitive in the counter mode. So if we use block cipher, then block cipher is a permutations. So we cannot get beyond the bar state security. But if we directly use the pseudo-random function in the counter mode, then we can prove the full bit security. So actually, the pseudo-random function is sometimes useful than block ciphers. So now we want to consider the most easiest strategy to generate pseudo-random functions from random permutation. So this is, I think, the very easy and simple constructions. So this side is an even Mansards. Even Mansard is, yes, this one. And we have 2 even Mansards, and so with using different random permutations and different secret key. So they prove this construction, sum of even Mansard, is secure up to order 2 to the 2n over 3 queries. So it's a beyond bar state security, so because this data is larger than 2 to the n over 2. And so this security bound is tight. This tight means there is a matching attack. So we can attack whose complexity is 2 to the 2n over 3. And how to do it? So we focus on this patterns. So x plus a1 is k1, and x plus a2 is k2. X is the input of the constructions, and a1 and a2 is the input of the p1 and p2. So if these 2 equations hold, what happens? So of course, b1 is output of the p1, and b2 is the output of p2. So b1 plus k1 plus y plus k2 plus b2 is always equal to 0. So then now we have k1 plus k2. So in the both sides, so the vx over x plus a1 plus x plus a2, and the k1 plus k2 is cancelled. And we have these last equations, y plus a1 plus b1 plus a2 plus b2 is equal to 0. So there is no key anymore. So we can use these equations as our filter, so that to detect these 2 equations. So how to do it? So how to recover the key? So we want to focus on x plus a1 is equal to k1 and x plus a2 equal to k2. But of course, the attacker doesn't know the secret key. So we don't know which x and a1 and a2 satisfies these equations because we don't know key. So now we construct we query to the constructions many times, and we can also query to the p1 and p2 many times. And in total, so that we query to the 2n over 3 queries to p1, p2 constructions. As a result, so we have 2 to the 2n over 3 times 2 to the 2n over 3 times 2 to the 2n over 3. So as a result, we have 2 to the 2n triplets, x, a1, a2. And as a result, for each k1, k2, so that we have these triplets. And so by using these queries, we can expect for one secret key, so that we have these equations. So now we want to simplify these constructions. So, but unfortunately, so there is many failed examples. So, for example, so the existing work already discussed some failures. So one thing is just use the same permutations, P1 is equal to P2. And another case is just using the same secret key. It means the K1 is equal to K2. For both cases, we have attack, whose complexity is the burst equality. So how to do it? So it's very simple. So if the both permutation is the same, then we query x and x prime. And so whose sum of the x plus x prime is equal to K1 plus K2. Then what happens? So the input of the up part and input of the second permutation is just swapped. Then the output of y and y prime is exactly the same. So then the attack strategy is very simple. So we just find x prime satisfying E of x is equal to E of x prime. So this is a collision. So now, so another failed case is the k is equal to k1 plus k1 equal to k2. So this case, so we want to observe this relationship. So and in that case, the output of y is equal to p1a1 plus p2a2 because the key is the same, so key is cancelled. So this case, so attack strategy is we just use the fixed a is equal to a1 equal to a2. Then we just query to the x and a, and we calculate the p1a plus p2a, and so computes the collisions. So it's a busted. Okay, so we have many failure simplification, but now we propose one successful simplification. So this is the answer. So the structure is very similar to the sum of even monsters, but we just skip the second key additions. So the simplification is only 2 last key exclusive over. So, but actually, so the intuition is very easy. So actually, so in even monsters, so the second key exclusive over is very important. So we never skip it. But this construction, so the sum of keyed sum of permutation construction, from attacker can observe the output y, but so the attacker never observes the output of the P1 and P2 directly, because these two values is XORed. So we don't need to add the secret key. So actually, so we prove the security bound. So, but this security proof is very, very similar to the sum of even monsters. But only the difference is this part. So now x plus a1 is k1, and y plus b1 plus b2 is 0. So actually, in sum of even monster, this 0 is k1 plus k2. So it's very easy to bound the number of the solutions satisfying these two equations. But now here is 0. So now we want to focus y plus b1 plus b2 is equal to 0. So now, so the y is random, because y is the output of the pseudo-random function, so attacker never choose y. So attacker want to get the y, so they just query to the x and just observe the y. But the b1 and b2, so this is the output of the random permutations, and the random permutation is invertible. So it's possible to query to the b1 and b2 and get a1 and a2 by computing p1 inverse and p2 inverse. So b1 and p2 are arbitrary, so can be chosen. Okay, so now so we define the set of y is the observed output of the keyed sum of permutations, and b1 and p2 is the set of the observed output of p1 and p2, so the chosen output. And now we say Q is the number of elements of the Y, and P is the number of elements of the B1 and B2. Then, okay, so now we want to bound the number of the triplet of the T satisfying Y plus B1 plus B2 is equal to 0, and Y is randomly chosen, and B1 and B2 is so can be chosen. Okay, so fortunately, so that we have existing papers. So that this paper say focus on the sum capture problem. So and this paper so say the bound. So and as a result, do Q query to the key to sum of permutation and P query to the P1, P2. So we can expect at most this triplet, and so the order to so that by adding so from this bound, so that we can prove that this construction can be secure with the 2 to the 2n over 3 queries. Okay, so the last part of my talk is attack. So again, so that we want to more simplify these constructions. So we prove if we use the independent key, this construction is secure up to the 2 to the 2n over 3, to the 3n over 3. But we want to more simplify, but how to do it? So one direction is introduced by Shinagawa and Iwata. So they use key k and 2k. So it's so 2k means a multiplication of the 2, so by 2, so it's my linear key schedule. And so that they have open questions. If so that they use this linear key schedule, so how to attack it? So actually, so the existing attack doesn't work. So now we want to attack these constructions, but and it's very non-trivial attack. And but as a result, we can find attack requiring 2 to the n over 2 queries. Okay, so the first we want to construct the set x a1 a2 such that for all keys there is x a1 a2 satisfying this relationship. So if this relationship holds, so b1 plus y plus b2 is equal to 0, so we can filter it. But how to find this relationship for all key only by 2 to the n over 2 queries? How to do it? So now spanned x is a set spanned by the element of x, and we now want to construct x a1 a2 defined like this. Okay, then. Okay, so now we want to multiply the gamma 1, gamma here, and the XORs, and we have these new relationships. Okay, so then x plus a1 is k. It means spanned x a1 must be universe, so that must be take all elements. But spanned gamma a1 and spanned n a2 and is chosen from spanned 1 plus gamma x. Then the second part is the 1 plus gamma x plus gamma a1 plus gamma a2. So the all elements can take from the element of this one. So we have the answer that this sum is 0. So now we convert these equations like this. Okay, so the first here. So we multiply the gamma inverse in the second one. So we have this one. And A1 is so used in the first element, and like this. And multiply gamma again, and like this. Okay, so now by using this relationship, we have this construction. So find x such that spanned x gamma x can take all elements, and we choose and in this case we choose A1 is 1 plus gamma inverse x, and A2 is 1 plus gamma x. Okay, so this is a simple example. So the n is equal to 8. So very simple one. So first we choose any gamma, and just multiply the gamma 2, gamma 2 to the 3, gamma 2 to the 4, gamma 2 to the 5, gamma 2 to the 7, blah, blah. Then we assign like this. So x is 1, gamma 2, gamma 4, gamma 6. Then gamma x is, of course, gamma 3, gamma 5, gamma 7. And this is, of course, take all elements. So actually, we have several cases. So for example, we choose gamma, but so the gamma 2, gamma 3, gamma 4, but the dimension is not 8, so on dimension becomes 4. Then we just choose additional u, and so like this. So the 1, gamma 2, gamma, gamma 3, and like this, so that we can have this relationship again. And actually, we prove several the lemmas about these topics. So for example, this dimension doesn't divide n, then this procedure doesn't work, but we prove we never have such case. And also, we choose u is not span of the distance, then these dimensions always double of the value dimensions. So now we know we choose x, and gamma x is like this. And so keep choosing linearly independent elements until the so all elements take span by the only n elements, then we can attack. So actually, this dimension is even, so that we just build x with one of two elements. But if this dimension is odd, so we have some another tricks, but it's very complicated, so just look at the paper. Okay, so finally, so that I want to reduce the time complexity. So actually, this attack is only shows query complexity. So query complexity is a birthday, but actually, so that if we want to execute this attack procedure, so that in practice, unfortunately, we need to find these three sum problems. But unfortunately, we don't have a nice algorithm to solve these problems. So currently, if we want to attack, if we want to execute this attack, we need 2 to the n complexity. But we have some trade-off attacks. So the online query is a birthday, but we query to the 2 to the 3n over 4 query to the p1 and p2 instead of the 2 to the n over 2. Then we have another algorithm for to solving the 3-sum problem. And this complexity is 2 to the 3n over 4. So in the total complexity can be 2 to the 3n over 4. Okay, so this is the conclusion of my talk. So please use the keyed sum of permutation, because this construction is exactly the same security level as the sum of even Mansell. And definitely, keyed sum of permutation is simpler than sum of even Mansell. But unfortunately, don't use the linear key schedule. Then we have attack. Okay, thank you very much.
So when you have two even Mansors with the same key, you apply a key after the permutation. If it's the same key twice, it cancels off, right? But what if you just have the key there just once instead of twice, so that it doesn't cancel with itself? Is that, I don't know if I'm explaining it well, but is that a variant that you considered?
So now you want to, wait.
Yeah,
sorry.
take your picture and make k1 equals to k2, and then also add y plus k at the end.
Yeah, so here.
Yeah, just on one of those, yes.
Yeah,
Not
and
on-
here. And
Yes.
so the k1, k2 again. So this case? Which case?
on the first one.
First one? Yeah, so if we use sorry. Okay, so if we use key additions here, so this construction was already proven by Crypto 2019 papers.
So I'm suggesting k1 equals k2.
K1 is equal to K2. Yeah, it's a cancelled. Yeah.
Yeah, but then I don't want them to cancel, so after the permutation, I just add k to one of them, but not to both of them, so they don't cancel. Yes. Yes.
Sorry,
Yeah,
feedback?
just Yes, just
K1 plus Y.
yes.
Yes. So actually, so the
It's no longer symmetric when you do that. So
yeah. So in that case, so that we just query to the, for example, so the x and x plus 1. Okay. So now we want to attack. Then how to do it? So that we query to the x a1 b a2, but additionally we query x plus 1 a plus 1 b plus 1. Then under so the sum of everything, then the output of the part key is cancelled, and we can construct a similar filter.
okay.
Yeah. So actually, I think that even if we XOR something, so even for example, so there's some new K3 and K4, we have attack.
Okay. Thank you.
Thank you for your talk. That was very interesting. I just wanted to ask, out of curiosity, so on the right, if we were to move the gamma k after P2 rather than before P2, would the attack still work?
Sorry, one more again.
Yeah, just if we were to move the gamma k after P2 instead of before P2.
Before P2, so the XOR here,
Yeah,
here,
yeah,
and remove here.
yeah. Would the same attacks work the same way, or would there be an even simpler attack? Or?
So maybe. Yeah. So actually, then. Yeah, I think it's maybe we have much simpler attack, but it's a bit complicated to explain from now. So actually, I haven't considered this situation.
Okay, thank you.
So then another try for the question. So have you considered the, yes, in the left-hand case, so what will happen if the P1 equals, just one permutation?
P1 equal P2,
Yes.
but there is a tag. So
That's attack,
Yeah,
okay.
possible and the text.
Okay, and so have you considered any possibility to make it, using the single permutation with some other fancy trick, additional? Beyond birthday. Yeah, still want to beyond birthday. Say using the inverse of the P1 instead of the P2, or these kind of things can be seen in the recent beyond birthday construction papers. So.
P2, if
Maybe.
yeah.
Maybe too much question.
Yeah, so for example, so it's a very interesting. So that if we use the P2 is P1 inverse,
Another try, another paper for the next year.
CTRSA 24.
Yeah,
So
that's a nice.
it's there is a possibility we have a trivial attack, but of course there is a possibility so that we can't hide attack. Yeah.
Okay, thank you. So then the second question is that, so you have attacked the right part, right?
Yeah.
And I would like to ask that is your attack can be extended to to the case where the other linear key schedule. I mean that the gamma k for some gamma in the finite field constant is attacked now, but then of course there are other possibilities for certain key schedule, some maybe fancier one. So does your attack capture the wider range of the key schedule?
So actually we have tried it so that we use the linear key schedule. Linear means some arbitrary linear key schedule. Then the theory is complicated, but the attack, as far as we try, so the attack is successful. So we can attack it. So, but we no longer use this type theory. This type theory. Then we need sort of more ad hoc challenge. But in many cases, we can find this type X. or even if we cannot find, so that we have some triand error, so that we can find x and gamma x and the linear L times x is almost spanned with all elements. So by correcting n over 2 or n over plus 1 elements, then we can find it. But yeah, so from a very related case, so that actually if we use a non-linear key schedule algorithm, then I don't know. There is, we can't mount any attack currently. So non-linear key schedule is one choice, but actually so that it's also very, very difficult to prove in the security in this case. Yeah.
Thank you very much.
Stop. Okay. Yeah, thank you very much.